Look at this machine. A traditional industrial robot is a marvel of immense strength and high speed, but it's completely blind to its surroundings. The problem with this rigid perfection is that it relies entirely on a static environment. If a physical part on the assembly line is misaligned by even a fraction of an inch, the robot doesn't know. It blindly executes its code, and in the process, destroys the part or snaps its own tool. This creates a massive bottleneck for businesses. When something falls out of alignment, operators must halt the line, run trial and error tests, and manually reprogram the machine. That level of strict environmental control might work in a closed factory, but it falls apart in human-centric industries. Hospitals, farms, and logistics centers operate in a chaotic, highly unpredictable reality. Upgrading the mechanical parts, installing stronger motors or faster joints, does absolutely nothing to bridge this gap. To actually bring automation into dynamic environments, robots require two distinct new abilities: sensory input to see the physical world, and a virtual imagination to plan their actions before they ever move a muscle. Start with a chaotic physical environment, like these randomly shaped objects tumbling into a logistics bin. This is where data extraction begins. The first step relies on a physical hardware layer. Industrial cameras and specialized 3D sensors are positioned around the workspace to constantly record high-quality visual data of the scene. But raw video is just light and pixels. The machine can't use it yet. The critical translation happens through computer vision algorithms, a software layer that instantly processes raw visual input. This process distills a physical item into strict mathematical data. The algorithm isolates a target, determines its XYZ coordinates, creates a bounding box, and calculates its precise orientation. This extraction happens in real time. If the object shifts, the visual data instantly updates, so the machine can now perfectly perceive the object. But visual data is effectively useless unless the robot has a safe way to figure out how to physically reach it. This is where a platform called RoboDK comes in. It acts as the robot's virtual proving ground, a digital twin where physical actions are simulated before they ever happen in the real world. Integration happens here. Spatial data from the vision system drops seamlessly into a blank 3D environment inside RoboDK. Using offline programming, the software tests dozens of robotic paths simultaneously. It discards failed routes, turning them red, until it isolates an optimized green path. Running these thousands of simulations offline carries immense operational benefits. It requires zero physical downtime, eliminates risk or damaging expensive equipment, and avoids constant manual human reprogramming. Once the simulation verifies that perfect route, the final execution step is remarkably simple. That singular, optimized path is sent back down to the physical robot. By bridging real-time vision with offline simulation, the entire trial and error phase is removed from reality. Now the physical machine executes the complex task with absolute precision and flexibility on its very first try. In manufacturing, a robot assembling intricate components can now detect micro defects through its cameras and instantly correct its own physical path mid-motion. In logistics, the simulation capabilities optimize entire warehouse layouts, while the integrated vision systems allow robotic arms to sort randomly sized, shifting packages without slowing down. In healthcare, this exact technology stack provides the extreme, sub-millimeter precision required for surgical assistance and automated patient monitoring. Look at this mechanical arm in an agricultural setting, smoothly navigating through thick, blowing leaves to reach a piece of fruit. The vision and simulation systems allow it to monitor crops and automate harvesting in an environment that changes every single day due to nature. Manufacturing, logistics, healthcare, and agriculture. These four vastly different industries are connected by a single demanding trait: chaotic unpredictability. By combining vision and simulation, the machine absorbs the complexity of its surroundings, navigating non-standard workspaces without requiring physical floor modifications. Achieving this level of intelligent automation does require heavy lifting. Integrating these systems is not a simple plug-and-play process. There are strict technological hurdles to clear. Engineers must ensure exact hardware and software compatibility, all while maintaining total system reliability as it processes massive visual datasets in real time. Overcoming these hurdles requires a dedicated human element. Companies have to invest in highly trained personnel to design the architecture, implement the code, and actively maintain the combined systems. But the baseline technology is advancing rapidly. Continuous improvements in AI processing algorithms and increasingly powerful, cheaper sensor technology will only deepen the capabilities of this integration over the next few years. Linking computer vision with RoboDK replaces blind repetition with a predictive workflow that adapts to the physical environment as it changes.